Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next episode in the Coding a 2D Physics Engine in Java series. In the last episode, what we did was raycast against circles. In this episode, we're going to finish the second half of that, which is raycast against boxes and rotated boxes. If you watched the line intersection versus box video, that should prepare you pretty good for what we're going to be doing in this tutorial. So that will be linked right up there. You should check that out if you haven't. But without further ado, let's check out the math behind this, and then we'll get to coding how to do an actual raycast against a box. Okay, so I've been staring at this for quite a while, and I'm going to try to explain it as best as I can. This one is quite difficult. If you've seen the OBB though, which is also called line intersection with a box, it's very similar to this. This is just a rotated version of that same problem, basically. So to solve this, if a raycast is intersecting with this box 2D, we see that we want to get this point returned, right? We want to get this point. Well, how do we get that? It's kind of difficult. So the first thing we can do, or the first thing we need a couple of helpful points. So we need the box's axes. So the box's axes we can think of as basically just which direction the box is rotated at. So if I draw a line there and a line there, it would be unit vectors in the direction of the box's rotation, okay? And we'll call these X and Y, okay? So this is X and this is Y. This box, by the way, is rotated at 30 degrees, so theta equals 30 degrees, just pi over 6. So we can call X, we can think of X as if it was just like a normal vector that looked like this, and then it had been rotated 30 degrees this way, and so now it looks like this, right? And it's a unit vector. It is a unit vector, so it's of length 1. Now, why am I talking about this? Well, that's because we're going to need another vector too. So before we move on, let's get the last vector that we'll need out of the way, which is going to be the vector from our origin to our center, okay? So using these three vectors, and we're going to call this one P. Using these three vectors, we can get most of the information that we'll need. So the reason we need the X and the Y axes is because we have a couple different points where our ray could be intersecting, right? So the points are going to be this bound, it's going to be this edge, and then it's going to be this edge, and it's going to be this edge, right? So it's just which edge of the box did we hit is basically what we're looking for. And so we can get that by looking at these axes and the projection of this P vector onto these axes. So what I mean by that is, let's just do a projection real quick. So let's imagine we're projecting P onto this x-axis. That would look something like this. It would go up like this, meet at a 90-degree angle. And if we build a triangle out of this, let's just draw the axis here because it'll make a little bit more sense. So if we draw a triangle out of this, this is our 90-degree angle, and this is our theta, which is the angle between the two vectors. So we'll call this X, and we have P, which is the green vector, and then we have this little edge right here, this little bit. So if we do P dot X, okay? So P dot X, we know that that's just the magnitude of P times the magnitude of X times cosine theta, where cosine theta we also know from SOHCAHTOA, once again, is just adjacent over hypotenuse. Well, what is hypotenuse in this case? Hypotenuse is P. It's the magnitude of P. What is adjacent? Well, adjacent is this big length here, okay? And so I hope you're going to start seeing where we can start getting some information from this. So if we substitute those in, so we'll say magnitude of P times the magnitude of X times adjacent, we just said, is this length here, and we'll call this length this is the length from here to here. We'll call that E of X, okay? So we'll call that E of X. So I'm going to get rid of some of this clutter just so that we can sort of see what's going on here. So we know that adjacent is E of X, right? So we'll say EX over hypotenuse, which we just said was magnitude of P. Well, that's just, those cancel out. We're left with the magnitude of X times the magnitude of E of X. Well, remember, X is a unit vector, which means it has a length of 1, which means magnitude of X is 1. 1 times E of X is just EX. So what we're left with is this big portion here, which is the direction along the x-axis, from the ray's origin to the center of our box. So this is going to be helpful in just a second, because think about this, okay? So if we have this length here, we can easily solve now, right? We know what this length is, right? This length is just half the box's length. This is 4. So what happens if we take EX minus half the box's X? Well, that gives us this length right here. And what is this length? This is the length from the vector's origin to this side of the box, right? And so we know that's really close to getting us to the length of, to our dot, right? This is almost to our dot, but we have to do one more thing. And that is we have to sort of scale the vector in the direction of our ray. And what I mean by that is, imagine for a second that the ray was pointing the same direction as this axis. So our ray was actually pointing this way, which is the same direction as this axis, which means it would look something like this, and it would hit the box right here. If they're parallel, if they're the same direction, then we have a problem solved, right? EX minus the size of the X's box will give us the length along our vector we need to travel. This is the length that we need to go. It would just be EX minus size X. We'll call that the half size, which gives us this point right here, this distance, which we'll call T. And that is our final solution, right? That is our problem that we're trying to solve. But we have a problem, right? Because our vector is not parallel. It's not directly parallel. It's actually skewed a little bit. And so what we can do to account for this skew is we can just take into account, sort of like we did, remember in the line intersection box when we were dividing by the normal X? That's basically just skewing it. We're scaling it with the direction of the vector so that we're like, okay, well, we know it's actually going to be a little bit farther out because we have to go a little bit farther out since the ray is pointing this way. And so what is that skew value? How much do we have to scale it by? And that's where the next part of it may not be so intuitive. And so the next part of it says we get our direction vector and we dot that with the X axis, okay? So our direction vector is this part of the ray, and the x-axis, once again, is this part of the ray. So you can think of it as this is the dot product, right? We're just dotting these two vectors together. And what this will give us is some, and I'm going to call this scale. We're just going to call this scale. And we can use this to scale our result, EX minus SX. If we divide by this scale, which is just D dot X, what we're going to end up getting is it's going to scale it appropriately so that we get this little extra bit. It's going to grow it a little bit. And then if the vectors were parallel, we would get D dot X for two parallel vectors. Remember, that's 1. So D dot X equals 1 if they're parallel, if these are pointing the same way. And what about if they're at a 90-degree angle? D dot X equals 0. So if we had two perpendicular vectors. And that makes sense too, right? Because if our ray was pointing the same direction, pointing perpendicular to our x vector, so if our ray was pointing this way, then we're never actually going to hit it, right? And so it would be an infinite value, right? So d dot x would be 0. We would be dividing by 0, which would give us infinity, which makes sense because we would never hit it. There's no way we could ever hit it. And so we're just going to get that infinity, which means, hey, you're never really reaching it. So it also makes sense then that if d dot x is anything between these two, it's going to give us the appropriate scale for any vectors between parallel and 90 degrees, which is what it does. So visually, this is what's happening. It's super confusing and it's super complicated, but this is just the way it works. And so what we're going to be doing is we're going to be doing p dot x, which will give us this distance from the ray's origin to this x center. And then if we subtract size x, we'll get the intersection point, the distance to intersection of the left side of the box. And if we do p dot x plus the size of the x, then we'll get the distance till we hit the right side of the box. If we do p dot y plus size of y, we'll get the distance from the ray's origin until we hit the top of the box. P dot y minus sy will give us the distance till we hit the bottom of this box, okay? And then if we do d dot x, it will give us the scale for our x, and if we do d dot y, it gives us the scale for our y. And now using these two bits of information, we can find the maximum of the minimums once again. So if we find the maximum of the minimum of these two, and the maximum of the minimum of these two, so the maximum of those, then that will give us the proper t-min, which we'll call, this is t-min. And the minimum of the maximums will give us Tmax, which is this point right here along the vector, as long as we are dividing too. So we find this, and then we divide this by d dot x. So this is division by d dot x division by d dot y, and division by d dot y. Okay, and so that will give us the length Tmin and Tmax, which is just the length from here to here and the length from here to Tmax. And then we can do the same sort of checks that we did last time, right? If Tmin is less than 0, we use Tmax because that means the ray has started inside since Tmin is behind it. And if Tmax and Tmin are both less than 0, then that means we intersected somewhere behind the ray. We did not hit the box. And I think that's all the edge cases that we have to worry about. And then if Tmin is greater than Tmax. If Tmin is greater than Tmax, then that means we did not have an intersection once again. But yeah, so visually, this is what's going on. It's a lot to take in. Watch the line versus intersection. I think I did a better job on that one. And this is very similar, but instead we have to sort of rotate it and scale everything according to these new axes that are the boxes. So with this little bit of an intro, let's actually code this and see if we can get it working. Okay, so I'm back in our project here. The first part of this is actually going to be pretty easy because we can literally just copy our line in AABB. So for raycasting against AABBs, I'm just going to copy this real quick. And we're going to go down here and we're going to say something similar to this. Basically public static boolean, and we're going to say raycast, and we're going to give it an AABB. This is our box. And then we want to give it our ray 2D and our raycast result. So ray 2D, ray, and raycast result. All right. So set it up the same way, and I'm just going to paste everything into here, except instead of a line.getStart like we have here, we're actually dealing with array, right? So we can get rid of that real quick. And then what we're going to do for our unit vector, we can actually just set our unit vector, that is just the ray's direction. So we can just say that's just the ray.get direction. And that should be good. Everything should be fine. And then instead of subtracting the line's start, we're going to subtract the ray's origin. So we'll say ray.get origin here. And once again, we'll do the same thing here, ray.get origin. And then down here, we just want to make sure that t is greater than 0 and t. So we'll say boolean hit equals t is greater than 0 and t times t is less than line.length squared. Or technically, we don't even need this. If your raycast has a maximum, like you don't want to hit anything beyond 5 units, then you would do like ray.get maximum here. And so we'll leave that in just for reference. But really, we just have to check and see if t is greater than 0. And so that's what we'll do. Then we'll say if not hit, return false, which should be good. And we also do want to do raycast result up here, dot reset result, so that we reset the result just in case they were looking for a result as well. And that will make sure it's a false value. Then we'll say if result does not equal null, we have our t value. This is how far along the ray we have to go. So we can say vector 2f point equals, and then we'll say ray.get origin. Actually, we'll say new vector 2f ray.get origin dot add ray.get direction dot multiply by t. And technically, this should be wrapped into new vector 2f2 because this is modifying that value. I'm going to do that just to be safe. I think there's a couple places where I have that as unmodified too, like up here. Yeah, so this should be wrapped in a new vector 2f2 in the circle method. I'm going to do that real quick just because it's better. And what is the normal going to be? The normal is just going to be the opposite of our point, right? Our vector to our point. So we can literally actually just copy the circle because this will still give us the correct result. So if we just copy that and instead of circle.getCenter, we're going to say point, we're going to say ray.getOrigin minus the point. Yeah, and that should work fine. So we use that, and then we'll say normal.normalize too. There's probably a better way to do this. I'm sort of making this up as I go because ideally we wouldn't want to have to normalize that, but I think, yeah, we normalized it up here too, so we'll just leave it with that. And then we're just going to initialize it once again, so result.initialize and return true down here. Okay, so that's AABB done. Not too bad. Now let's get into the hard stuff, which actually isn't that much harder. I'm just going to copy and paste this real quick, and we're going to call this box 2D instead of that. So this is mainly going to be the same with a couple differences. You know, I'm just going to erase all this though. So get rid of all of it. We're starting fresh. So first thing we're going to want to do is we're going to want to get our x-axis and our y-axis. So let's just make a new vector 2f. X-axis looks like this. Vector 2f, y-axis looks like this. 0, 1. These are unit vectors. And now we'll rotate them. So we'll say jmath.rotate. We want to rotate x-axis, and we want to rotate it by our box.getRigidBody.getRotation. And we want to rotate it about 0, 0. Because this vector is centered at 0, 0. Remember, this is just some vector we made up. So we want to make sure we rotate about 0, 0 as well. Do the same thing for our y-axis. Box.getRigidBody.getRotation. We actually want to do negative too. I always forget that. Negative because we want to go in the opposite direction just to make sure we're rotating the correct way. I believe, I might be wrong about that, but I think negative is what we want to do. You guys will find out when we go to test this code. So we have our x-axis, we have our y-axis. That's good. We also want that p vector and that f vector that I was talking about, or p. Let's get p first, okay? Because that one's not too bad. So p is the new vector 2f, box.getRigidBody.getPosition.sub ray.getOrigin. So that's p. That's not too bad. Now we want to project the direction of the ray onto each axis of our box. And so we're just going to store this in a vector itself. So we're going to say vector 2f, f, and we're just going to say this is a new vector 2f, and you'll be able to see what I mean here. We're just going to say x-axis dot dot p and y-axis dot dot p, right? So we're doing exactly what we talked about. We're just dotting it, so we're projecting it onto p, project onto p. We're just storing it inside of this vector for ease. And then next, we're going to project p onto every axis of the box. So we've projected the direction, and now we're projecting p, so we're getting the second half of that, and that was what we called e, right? Ex and ey. And we'll call this new vector 2f, and we'll just say this is x-axis dot dot, and this is going to be p, and then y-axis dot dot p. Okay? So nothing too fancy going on there. If you look at the calculations we were doing in the math, this is the same thing. Once again, we're just storing it in a vector just for ease. It's nothing too big. Okay, and the way we're going to do this is we're just going to loop. Well, first of all, we're going to say t float array t equals 0, 0, 0, 0. And these are just the min and the max value. So this is min x, min y, max y. You can think of these. These are the same things. Remember, we did the min vector and the max vector. We have 4 floats. Same thing here. We're just storing it in this array instead. Because now what we're going to do is we're going to say for int I equals 0, int I is less than 2, I plus plus. So we're going to loop through each axis of our box, okay? And if we talked about how we could have parallel vectors. So if jmath.compare f.get I 0. So f is the dot of our axis to p. And this should be direction. This says x-axis to p, x-axis, and that's the same thing we have here. So I'm sorry. This should actually be ray.get direction. And this should be ray.get direction. Okay, so once again, in our f, we have x-axis dotted with the ray's direction. So if the ray is parallel with either axis, that means that we could have a potentially divide by 0 error. And so if the ray's origin is not inside of the box, then we know it's not actually going to hit the box. Because if it's parallel with one of the axes and it's not actually starting inside the box, then there's no way it's ever going to hit the box. So we'll say if the ray is parallel to the current axis and the origin of the ray is not inside, we have no hit. Okay, so then we can exit early. So we'll say if negative e dot get I minus size dot get I, and we'll get that size variable in just a second, is greater than 0, or negative e dot get I plus size dot get I is less than 0, return false. And so what we're doing here is we're just basically checking to see if the length from the vector's origin to the box's edge is less than the half size, or is not within the half size, then it's outside of the box. And so we're just checking that here with this less than 0 and greater than 0. And we'll say vector 2f size equals box.get size. And actually this is going to be half size. Let's go into our box 2D real quick and create that function just so that we can use it. We'll say public vector 2f get half size, return this dot half size. Okay, back into here. So now we have no errors, we're good. Next, what we're going to do is, otherwise, if it was inside, we can still use this, but we have to make sure that we say f.set component I to 0.00001f. So we set it to small value to avoid divide by 0. In this case, too, what would happen is it would be turned into infinity if we divided by 0, which still isn't good. So we just set the component of our f vector to a small number, and that should fix that. Okay, and then what we're going to do is we're just going to say ti times 2 plus 0 equals e.getI plus size.getI over f.getI. So tmin for whichever axis we're on. So 0 would be x and 1 would be 2 for I. And then ti times 2 plus 1 equals e.getI minus size.getI over f.getI. And this is t max for this axis. And actually, I think that's backwards. I think this is t max because we're adding here. So this is t max, this is t min. Okay, and this is half size, not full size, half size. Okay, and now to find the true t min and the true t max, we need the maximum of the minimums. So we'll say t min, this is the true t min, is math.max of the minimums. So we'll say math.max of math.min, and we're going to say t0 and t1, and math.min of t2 and t3. Okay, and then float t max is going to be the minimum of the maximums. So we'll say float dot, it's the math.min of math.max, t0, t1, and math.max of t2, t2, t3. And that's our true t max to t min. Then we can basically do the same thing that we did here. I'm literally just going to copy this because it's the same problem at this point. So then we'll just say t equals t min less than 0, blah, 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 all that stuff. I'm going to change this to t array so that we know that this is our t array. Copy and paste that everywhere. That we had a t just to fix the errors, because that can be a little bit confusing. This is just an array of t values. It's not necessarily the t value. This is the t value. Okay, and then we basically do the same thing that we did down there. It's the same problem at this point. This is a tough one. If you don't completely understand it, it's okay. If you do, please double check my work, because I'm 99% sure that this will work. We're going to have to write some good unit tests to make sure this does work correctly. But yeah, this is raycasting against a rotated box. Raycasting against a regular box is actually a lot easier. Once again, check out that video. It makes a little bit more sense than this one. I hope you guys liked this. If you did, please hit like and subscribe, and I'll see you in the next tutorial in which we will start talking about shape versus shape. So checking to see whether two shapes are colliding. We've sort of built up this groundwork. Now we're ready to get into a little bit more heavy duty work where we can start dragging shapes into each other and telling when they are hitting each other and everything. So I'll see you guys then. Thanks for watching.